a student of International Institute of Professional Studies, Devi Ahilya Vishwavidyalaya, Indore. In this video, we will be solving the end semester question paper of the session 2023 of the subject Numerical Analysis and Design. So let's get started. The first question is, find the roots of the polynomial x square minus x minus 1 through fixed point iteration method. Also make a table for various possible equations shown and show nature whether they are convergent or divergent in nature. So in this question, we will be assuming that the f of x will be x square minus x minus 1, that is the given polynomial, and f of 1 will be negative and f of 2 will be positive. Uh, this we can get by putting the substituting the values 1 and 2 in the equation. So f of 1 will be negative and f of 2 will be positive. So the root is between the points x 1 to 2. That is the value of root will be in between the 1 and 2. So now we have to take the median value of the two in between the 2 points. So the median will be 1.5. So we can take, we will be taking x0 as 1.5. So by substituting the values here, the following equation g of x that can be made through f of x, we have made the table for the value of f of x, g of x will be this, g dash of x will be this, that is 1 upon 2 root over x plus 1, and so the absolute value of g dash of 1 will be less than 1 and the absolute value of g dash of 2 will be less than 1. So in this we have um, calculated the values for various points. So for correct value of g of x, we have to consider that the g dash x, the absolute value of g dash x should be less than 1. And if the multiple value of g of x are less than, then choose the least value. So we have to choose the least value. So this is the table of convergence. If both the values are less than 1, it is convergent. If they are greater than or equal to 1, they are divergent. 1 is greater than equal to 1 and g dash of 2 is less than equal to 1, then also divergent. The convergent case is only when both of the values, that is at g dash of 1 and g dash of 2 are less than 1, then only it will be convergent, otherwise it will be divergent. So here we have taken g of x equals to root over x plus 1, which is for fixed point iteration method, and the points in which the root exists are the 1 and 2. So the median value will be 1.5. So we have considered x0 as 1.5 and then x of 1 as putting 1.5 value in the equation g of x. So that will be x of 1, and then in x of x2 we will be putting the value of x which we have obtained as x of 1. So in this way we will be putting the previous x of something values, uh, and at the x7 stage the value is 1.6179 and at x8 it is 1.618001. So the error between x7 and x8 is 0.000101. Hence the root of x square minus x minus 1 will be x of 8. So this will be the final answer for this question. The root for this equation is 1.618001. So moving on to the next question, which is we have to find the solution of system of equation using iterative method. So the equations are 20a plus b minus 2c equals to 17 and 3a plus 20b minus c equals to minus 18, and the third equation is 2a minus 3b plus 20c equals to 17. So we will be using the Jacobi method for solving the equation. In this method, we will be substituting the values obtained in the previous stage, and we will find the values of a, b and c in the respective equations by taking the variable from variable to the one side. So we will be getting an equation for each variables given in the equations. So that's what we have done here. We have taken the variable one side and all the other values to the other side. Similarly for b and c also. Uh, at the first stage, that is a, at the zeroth stage, we will be taking all the values, that is a0, b0 and c0 as 0, and we will be substituting the values in the equation we made for the variables. So the answers, whatever answer we have got in this stage, will be used in the next iteration. That so a of 1 will be the value obtained at the a of 0, not the value which we have taken at the 0 stage, that is 0. We'll be using the values of previous stages. So that's what we have done here. We have substituted the values, and then again we will be repeating the same process for a of iterations also. That's what we have done for A2, A3 and A4. Sorry, for B4, C4 too. That's what I meant. So we will follow up these steps till we get the repeated approximate values. So at the point at which we start getting the repeated values, which are all approximately same, that will be the final answer, that is solutions for the given equation, that will be the values of A, B and C. The next question is, list out 4 disadvantages of Gauss elimination and 3 advantages of iterative methods over elimination method. So the iterative method is superior to the elimination method due to its computational effort, which is approximately 2n raised to the power 2 arithmetic operations per iteration, and if convergence is achieved in less than n iteration, it is significantly superior compared to the elimination method. The another advantage will be the iterative method is has small rounding errors. So the rounding error being the one committed in the last iteration, thus for ill-conditioned system, an iterative method will be a good choice. In Gauss-Seidel method, we set x of I equal to newly calculated value of the iterate stored in temp. So we substitute the values obtained in the same step only. So it reduces the computational efforts and number of steps in which we will be getting the final answers. So the disadvantage of Gauss elimination are the computational effort is approximately 2n cube by 3 arithmetic operation in each elimination step, and the amount of bookkeeping necessary is considerable. Any special structure in the matrix of coefficient is difficult to preserve during elimination, and the rounding errors may become quite large, particularly for inconditional equation. So you can read the points again. Moving on to the next question. We have to write the algorithm for Lagrange's inverse interpolation. So for Lagrange's inverse interpolation, we will be reading the number of inputs, that is n, and we'll be reading the values of x for from starting from 0 to n minus 1 iterations. We'll be reading the values of x and y for at each iterative step. Then we will taking a variable sum and set it to 0, and from lowest to highest uh, values, that is from 0 to n minus 1, we will be setting the product 1 and then again taking a nested loop that is for j, which will also running from the lowest to highest values, that is 0 from n minus 1. And whenever we will be finding the values I and j as equal, we will be setting the product for that step, that is product equals to product star y minus y of I upon y of I minus y of j. The only difference in the inverse and Lagrange's in interpolation is the at the mm, point where we have taken y, we will be taking x. That's only the difference at the product equation. And then finally we will be adding the sum by multiplying the coefficient, that is x of I, to the product. And by performing all the iterations, we will be printing the sum. Is evaluate the integrate of 1 upon 1 plus x square using the 3-point Gauss quadrature formula for the given abscissa and weights. So we have the values T1, T2 and T3 and W1, W2, W3. So T1, T2, 3 are the abscissas and the W1, W2, W3 are the weights. So this is the formula for 3-point Gauss quadrature is x equals to b minus a upon 2 into t plus b plus a upon 2. So this is the formula, and we will be assuming the initial values of a and b as 0 and 1 respectively. Then substituting the values in the equation, we will be getting x equals to 1 plus t by 2 and d of x equals to d2 by 2. dt by 2, sorry. And then we will be taking f of t as the value of x and dx in the f of x. So f of t equals to integrate of from minus 1 to 1 of 2 upon y plus 1 plus t whole square dt. So by solving this equation, we will be getting the final answer as 0.78527. So this will be the final answer for this integrate. This makes the process simpler and faster to execute in the also decreases the computational efforts. Next question is write an algorithm for the Weedle rule for 6 points. So the algorithm will be, we will be taking the start value, then reading the end value, and then we will set the height, that is end minus start upon 6. So Weedle rule is for we have given for the 6 points, so we will be dividing it by 6. Then from lowest value to the 6, we will be reading the values of y for each iteration, and then by using the Weedle's rule, we will be setting s equals to 0.3 into h into y0 plus 5 y2 plus 6 y3 plus 4 y4 plus y5 in such a way. And then finally we will be printing the values s. Next question is write algorithm for Range Kutta fourth order method. So in this method, we will have to take a function which we have defined as f, passing the parameters x and y respectively, and we will be returning the expression. First of all, we will be reading the starting point, ending, and the number of splits, from which we will be calculating the value of h, that is ending minus starting upon number of splits, which we have taken as input. Then we will be taking a while loop which runs until for each iteration, that is from start to end. As soon as start becomes end, the loop will be terminated. So the K1 is calculated as h into f, the function called, whatever the expression will be written will be multiplied by the value h. In such a way, we will be calculating K2, K3 and K4 also. and at the end we will be setting x equals to x plus h and starting equals to starting plus h, and the value of y will be summing k1 plus 2k2 plus 2k3 plus k4 divided by 6. So this is the algorithm for Range-Kutta fourth order method. And at last we will be printing the values x and y respectively. Next question is, apply predictor corrector method to solve dy by dx equals to minus xy comma y0 equals to 1 in steps of 0.1 to y of 0.2. So this is the solution for the predictor corrector method, which we have, that is Hyoon's method, which is also called Hyoon's method. So y of 0.1 will be 0.997 and y of 0.2, that is the predicted value and the corrected value we have mentioned here. So we can apply the corrector formula again for more accurate value by putting this corrected value as predicted value in the corrector formula.